In this important lesson, we discuss antiderivatives. So what we'll do is we'll start with the function f, and we want to find a function, capital F, whose derivative is f, meaning the derivative of this uppercase or function f is f. If I take the derivative of f, capital F, I get lowercase f. So if this function, capital F, exists, it's called an antiderivative of lowercase f. Okay, so antiderivatives are the link connecting the two major elements of calculus, derivatives, which is what we've been studying, and definite integrals. So let's start with a formal definition for an antiderivative. So here we have the formal definition for an antiderivative. A function f is an antiderivative of lowercase f if the derivative of capital F is f of x. F prime of x is equal to f of x, okay? So this would be called the antiderivative because if I take the derivative, I get f. You're going to see that common notation is to use a capital letter like F or a capital G. Capital letters are most often used to denote or to represent an antiderivative of a function. So let's look at this first example. We're asked to find an antiderivative for each of the following functions. So the first function we're considering is f of x is equal to 2x. We need to find a function such that when I take its derivative, I get 2x. Find me the function such that when I evaluate the derivative of that function, I get 2x. So we definitely have to work backwards. So you should use your skills of differentiation to figure out that this must be x squared. This must be the antiderivative. How do we know that? Well, check it. Take the derivative of capital F of x is equal to x squared. The derivative of this function would be equal to f of x equal to 2x. So this here would be called the antiderivative. And then just to prove it to you, f prime of x would be equal to 2x, which is equal to f of x. So there you go. We can prove it, If I find the derivative of capital F, I get lowercase f. So this is definitely right here. This is the function whose derivative is f of x. So this is called the antiderivative. Okay, the next function they want us to find, they want us to find the antiderivative for is g of x is equal to cosine of x. So I'm looking for the antiderivative whose such that the derivative of the antiderivative is cosine of x. So it's going to be capital G, right? Capital G of x is equal to sine of x. How do we know that's true? Well, because if I take the derivative of capital G of x, that would be equal to cosine of x, because the derivative of sine of x is equal to cosine of x, right? And this is equal to g of x. So this for sure is the antiderivative. Sine of x is the antiderivative for cosine of x. Again, because if I take the derivative of sine of x, I get cosine of x. So this is our answer right here. All right, this is the antiderivative. All right, very good. All right, the next function is h of x, and it is equal to secant squared of x plus 1 over 2 root x. Now, I'm just hoping that by this point, you're familiar with this function, secant squared of x. You know that tangent of x, the derivative of tangent of x is secant squared of x. And 1 over 2 root x, the derivative of the square root of x is equal to 1 over 2 root x. So then this must be the antiderivative. Now, earlier we found the following. F of x equal to x squared is the antiderivative for f of x equal to 2x. How do we know? The derivative of this function gives us 2x. So this is the antiderivative, but it's not the only antiderivative. And that's because I can find another function whose derivative is 2x. For example, how about this? X squared plus 1. What's the derivative of this function? Well, the derivative of this function would be just 2x, right? Because the derivative of 1 is 0. So this function also has a derivative that is equal to 2x. Wait a minute, I could come up with another one then. How about f of x equal to x squared minus 3? What's the derivative of this function? The derivative of this function is 2x. I can give you another one. F of x is equal to x squared, I don't know, plus 5. The derivative of this function, which is different, right, is 2x. So you can see all of these are antiderivatives, and they all differ by just a constant c. These constants we're going to call capital C, and we're going to say that's just an arbitrary constant. So what we can say is there are more than one. There are actually many antiderivatives for 2x. All of the antiderivatives of 2x just differ by a constant. So we have that if capital F is an antiderivative of f, function f, then the most general antiderivative is f of x plus c, where c is just an arbitrary constant. Okay? So now check out this example here. Find an antiderivative of the function 3x squared that satisfies f of 1 is negative 1. Now, since we are given this function 3x squared, we know that x cubed, we know this, x cubed, if we take the derivative of x cubed, we get 3x squared. So then this is going to be our antiderivative right here, x cubed. So then this is what we have. Capital F for, to denote an antiderivative, capital F of x is equal to x cubed, and then watch this, plus some constant c, because all of the antiderivatives for 3x squared just differ by a constant. Now, we need to satisfy this condition that when you plug 1 into your antiderivative, you get negative 1 out. So that's calling on a specific antiderivative. All right, so let's do it. So then we have f of 1 would be 1 cubed plus c, right? Which is equal to 1 plus c. Now, they're telling us that f of 1, the output needs to be negative 1. Okay, so that would imply that negative 1 is equal to 1 plus c, right? Which implies that that constant must be negative 2. So now we can update this, folks. Our antiderivative is going to be x cubed minus 2. Let me write that down. Move this up just a little bit. So this is our final answer. The antiderivative that they're looking for is x cubed minus 2. This is the antiderivative, that the specific antiderivative that they're asking for. Okay, folks, so now we want to find the general antiderivative of each of the following functions. So this is the first function we're considering. F of x is equal to x to the 5th power. So we're going to need to find that polynomial function such that when I take its derivative, I get x to the 5th. So then this is going to have to be capital F of x is equal to, watch this, x to the 6th over 6. Let's confirm that really quickly before we move forward. The derivative of the antiderivative should give me x to the 5th. So it'll be the derivative of x to the 6th over 6, right? So by the power rule, we know that this 6 in the power comes down. So then it's 1/6 times 6, and now it's x to the 5th power, which is just x to the 5th power. And this is definitely equal to f of x. So what I just confirmed for us is that this here is indeed the antiderivative. Now, they want the general antiderivative. Okay, so let's go back here and add a constant. Because remember, all of the antiderivatives for this function, x to the 5th power, will differ by just a constant. So you tack on, if you will, c on the back end here to get the general antiderivative. So here's our final answer here. This little formula will be helpful if this is the function that they're giving us, some polynomial function raised to the power of n here, then the antiderivative will be x to the power of n plus 1, all of that over n plus 1. Like, for example, they gave us x to the 5th, and what is the derivative? X to the 5 plus 1, which is 6, all over 5 plus 1, which is 6. So this formula here can help you find the antiderivative for any function that's of this form. Now, in order for it to be a general antiderivative, you need plus c here for any constant. Okay? Okay, folks, this is the next function that they gave us. G of x is equal to 1 over square root of x. You can rewrite this as x to the negative 1/2 power. Yes. And so now we can use that little formula that I gave you just a moment ago. So capital G of x, this is the antiderivative, will be x to the power of negative 1/2 plus 1 all over negative 1/2 plus 1. So let's simplify. This will be x to the power 1/2 all over 1/2, which is equivalent to 2 times root x. This here, folks, is the antiderivative, but in order for it to be the general antiderivative, I need to tack on c for that arbitrary constant. So this is the general antiderivative. All right, our next function is h of x is equal to sine of 2x. Now, first of all, we have to keep in mind, let's see, capital H for our antiderivative. Now, we know that the derivative of cosine is negative sine. The derivative of cosine is negative sine. We have positive sine. So that must mean our antiderivative looks like negative cosine. Right, everybody? Because the derivative of negative cosine will be negative sine, which is positive sine. So first of all, negative cosine is how this works out. Now, we're going to need 2x and then all of this over 2. Okay? So let's see if we can confirm this. All right? So h prime of x. Supposedly, you get sine of 2x when you take the derivative of this. Okay? So let's confirm that really quickly. First of all, you can say that this is negative 1/2, right? We're negative, and then 2 in the denominator. That's negative 1/2 as a constant multiple. And so really, you're just doing the derivative of cosine of 2x. Now, the derivative of cosine of 2x is negative sine of 2x. And then by the chain rule, it is times 2. Right, everybody? So then a negative times a negative is a positive, and then this 2 here and that 2 cancel out, and all you're left with is positive sine of 2x. You see how that works? So then this for sure is the antiderivative. Oh, we need to tack on c, don't we? For an arbitrary constant. So now this is our general antiderivative for this given function. Okay, our next function, I of x is equal to cosine of x over 2. All right, so we need a capital F here, a capital I here for the antiderivative. Now, we need to find the function whose derivative is cosine. Well, first of all, that's going to be sine, right, everybody? Sine, the sine function, is the function whose derivative is cosine. I'm going to keep the same argument, so sine of x over 2. Now, over 1/2. Now let us, and then plus c. Let's confirm that when you take the derivative of this antiderivative, that you indeed get the original function. All right, here we go. Now this divided by 1/2, that is equivalent to multiplying by 2. And I'm going to take that 2 as a constant multiple. So this 2 is this dividing by 1/2. It's the same. So now I'll just take the derivative of sine of x over 2. The derivative of sine is cosine of x over 2. Now by the chain rule, it's times 1/2. And don't forget the derivative of a constant is 0, so that's gone. And notice how this 2 and 1/2 cancel out, and you are left with cosine of x over 2, our original function. So I have shown that this here works for my antiderivative. But you know what? Before I box it, I wonder if we should simplify this a little bit. Let me see if I can make room for us really quickly by erasing. I have proven that when you take the derivative of our antiderivative, we get our original function. All right, cool. What I wanted to do is just simplify. So our antiderivative is 2 times sine of x over 2, and then plus c. This is our general antiderivative. Now we have a very important definition here. If we collect all of the antiderivatives of a function, that's called the indefinite integral of a function of f with respect to x. And this is how we write it. This is the integral, the indefinite integral of a function f of x dx. Okay, this is called the integral sign, integral. This function right here, f of x, is your integrand, and x is your variable of integration. And that's what this is showing. Dx is telling you your variable of integration. Now, now we can use this notation to help us. So watch this. Let me see if I can, yeah, watch this. The indefinite integral of 2x dx. What this means is I want all of the antiderivatives of 2x, of this function. This is your integrand. This is dx. This differential is telling you the variable of integration, which is x. And so all of the functions whose derivative is 2x is going to be x squared plus c. Remember that c is just some arbitrary constant. So this is the collection of all of the antiderivatives. This is the indefinite integral. Okay, I'll give you another example really quickly before we move on. The indefinite integral of cosine of x dx will be the collection of all of the functions, all of those antiderivatives, right? All of the functions whose derivative is cosine of x. So that's going to be sine of x plus c. All right, very good. Make that look like an x there. All right, here we are asked to evaluate an indefinite integral. X squared minus 2x plus 5 is your integrand. You want to find all of the antiderivatives for this quadratic function. All right, so what we can do is we can integrate term by term if we wish. So what we can do is the integral of x squared dx minus the integral of 2x dx plus the integral of 5 dx. Now, when you look at this function here, this is of the form x to the power n that we mentioned earlier. So then the antiderivative will be x to the power of 2 plus 1, which is 3, over 2 plus 1, which is 3, minus what we can do here is you can pull out that 2, and this is equivalent to 2 times the indefinite integral of just x dx. Plus, now here, you want the function, right? This is asking you for the function whose derivative is 5. Well, that would just be 5x, wouldn't it? If you take the derivative of 5x, won't you just get 5? So this must be 5x. So the only last piece is this one, but this is still of the form x to the power of n, where your n value is 1. So then this is x cubed over 3 minus 2 times, then this will be x to the power of 1 plus 1, which is 2, over 1 plus 1, which is 2. Of course, we want to simplify this 2 and that 2, and then what that gives us is x cubed over 3 minus x squared plus 5x. Now, be careful here, plus c. You never want to forget that constant at the back end. Remember, all of your antiderivatives differ by just a constant. So be careful to always include that constant.